Hello and welcome to this complimentary webinar in the series of webinars aimed at discovering the geometric suite of data analytics solutions. This is the second part out of 11 and today's title is Robust Optimization. My name is Lennart Eriksson and I work for Sartorius Stedim Data Analytics Solutions. The roots of Sartorius Stedim Data Analytics go all the way back to 1987 when Professor Svante Wold and Professor Rolf Karlsson founded a company in northern Sweden initially called Umetri, which later became Geometrics and these days Sartorius Stedim Data Analytics. And today we're fortunate to have Professor Johan Trygg on board to continue to drive the innovative efforts. We are a business solution provider in the fields of advanced data analytics, and our mission is driving growth by enabling our customers to see what others don't. And our vision is to be recognized as the leading data analytics solution provider. Our solutions are realized through the so-called geometric suite of data analytics solutions, which comprises the softwares Modde, Easy Analytics, Simca, Simca Online, Control Advisor, and Active Dashboard. In the first webinar in this series, we started to get familiar with the Modde software for design of experiments, and part one was an introductory account of the topics of DOE. Today we are going to go into a bit more detail into the data analytics capabilities of the Modde software in terms of tools for robust optimization, design space estimation, and quality by design functionality. Here is a little outline of today's presentation. We're going to discuss the problem. We're going to consider what we mean by the term optimum, what is robust optimization, some terminology. There will then be a demonstration of a case study drawn from our tutorial examples from our course material, and towards the end there will also be some concluding remarks. So the case study that we will study in this presentation is an optimization case that for those of you that have attended perhaps trainings or other webinars is known under the name of Truck Engine. The original investigator is Sven Alinder, and we want to acknowledge him and thank him for providing us access to this data set. Sven is working within the Volvo organization, and within the Volvo Car Corporation and Volvo Truck Corporation, DOE is commonly used in the early stages of new engine development, and very common goals are to operate the engines in an environmentally friendly manner, meaning that it is important to reduce fuel consumption and also reduce level of undesired species and exhaust gases. And the experiments are often done in environments where they have very good, where the engine engineers have very good control over the experimental procedures. So the engines are tested in front of or under simulated traffic, varied simulated traffic conditions, waiting times in front of traffic lights, acceleration, retardation, overtaking, mixed driving on the countryside, in the city, and so on and so forth. So when we enter into the story, screening designs have been used, and we are now in an optimization case where there are three factors in the problem. First of all, the first factor is the air mass entering into the engine. You can call it the feed. We have the exhaust gas recirculation, varied between 6 and 12%, and this exhaust gas recirculation principle is used to lower the engine temperature and thereby hopefully reduce some of the levels of NOx in the exhaust gases. The third factor is called needle lift, and it has to do with the timing of the fuel injection in relation to the movement of the piston in this piston engine. There are three responses that are measured: the fuel consumption, which is measured in a unit as milligram per stroke of the piston, and the amount of NOx species in the exhaust gases, which is measured in the unit milligram per second, and the amount of particulate soot matter in the exhaust gases, which is also expressed as milligram per second. The interesting thing is that there are specifications for these responses that are set by mostly by legislations, and the limits here are that fuel should be below 250 milligram per stroke of the piston engine. The amount of NOx should be in the exhaust gases should be below 25 milligram per second, and the amount of particulate soot matter should be below 1 milligram per second. When we are doing DOE, and as we were discussing in the first webinar in this series, one of the main aims is to lay out experiments so that we can estimate reliable contour plots, reliable maps of the system. And without going into all the details, we can just conclude that these are the sort of reliable maps that can be estimated and produced in this truck engine application. So in the top left plot, we see how fuel is predicted to change when we're changing the factor air and EGR. In the top right contour plot, we see how NOx is predicted to change when we are varying the same two factors. And in the lower left-hand part, we see the third response, soot, how it is predicted to change when we're changing air and EGR in this experimental design. And whenever we have specifications and they are, so to say, applicable and relevant in a certain contour plot, their position is emphasized by a slightly thickened black line in the contour plots. So we see that here we have the upper maximum setting for fuel, and so we should, according to fulfilling the specification, be below this line, basically following the black arrow to satisfy the needs or the demands for the fuel response. To satisfy the specifications for the NOx response, we should basically be to the right of this line, following the black arrow, and the specification for soot dictates that we should go along this black arrow. So we can clearly see there are conflicts with regards to the latter two responses, NOx and soot, and that is also possible to see if you are just plotting the original experimental measurements. In this scatter graph, we see that we cannot simultaneously minimize both soot and NOx because they are inversely correlated. A much more favorable situation would have been the case if these two responses would have been positively correlated, indicating by a data distribution along this diagonal. So there is clearly a conflict. Another type of plot that is often used in these circumstances is a so-called sweet spot plot, which is an overlay of the different response contour plots and color coding according to how well you fulfill the specifications on the responses. And the basic principle underpinning this type of plot was presented in the first webinar, and I refer to that recording for more details. Here we see the sweet spot plot arising for the truck engine application, and we can see that we definitely have a green region where the specifications are fulfilled for the different responses. The green area, the sweet spot area, is to the left demarcated by the upper maximum setting for NOx. In the top and slightly right-hand part, it is demarcated by the maximum setting for fuel, and in the lower right-hand corner, it is demarcated by the maximum setting for soot. So the question is now, where should we operate the engine over time? Should we operate at this coordinate, for instance? Should we regard that as an optimal position? Well, it could be argued that if we are preferring to have very little NOx in the exhaust gases and the low fuel consumption, this could be a good coordinate for running the engine. The problem is that we are very close to the maximum setting for soot. Or should we go over here and opt for a good combination, a good balance between the different specifications, where we would have relatively high fuel consumption and fairly large amounts of both NOx and soot in the exhaust gases? Or maybe this coordinate is to be preferable, where we are sacrificing on the NOx side, you can say, by allowing comparatively large amounts of NOx, but little fuel consumption and little soot. Well, it's not very easy to know where to maneuver unless you have set specifications and priorities. And another thing that is often also overlooked or ignored in the context of optimization is what we call the safety margin. Going back to the first point that we were discussing, it is so that if you start to perturb this system and take into account all the different uncertainties that can occur in DOE, factor precision, model uncertainties, and other sources of variations that may indicate the instability of the system, you realize that if you would be at this coordinate, there is up to around 20% or maybe even greater risk that you would violate the maximum setting for SUT. In the histogram here that is inserted, we see the result of 1 million predictions at this point based on Monte Carlo simulations, and we can see that in a rather large proportion of these predictions are actually risking of exceeding the maximum setting. So clearly we are very, very close to the border in this case, and maybe the safety margin isn't large enough, and this red dashed line should probably be over here for us to consider this as a more safe coordinate. So the consequence of this safety margin and risk assessment investigation is that we have to go closer to the center part of this sweet spot plot, and we're now going to discuss more how to accomplish this. So as you see here in the alternative plot that the Model 12 software can provide, which we call the design space plot, which instead of coloring according to how many specifications are fulfilled, is color coded according to the probability of failure to comply with the response specifications. We see that the risk is somewhere between 10% and 50%, and if we zoom in on the details, it's around 25% or so. This coordinate is clearly in a very high risk area, and this is not a recommended point at which to operate the engine. A much better situation is to go for a coordinate that is located in the green colored region here, which is a region where you have a very low risk, a smaller than 1% risk of failing to comply with the specifications. And this point is located at the center of gravity of this green region, and it is labeled the robust optimum inside the Model 12 software. The robust optimum has maximum distance to the borders of the design space area or design space volume, and this is in a robust optimization sense a point to be preferred over any other point that is located on this response surface. So what we're trying to say is that there is a difference between an mathematically optimal point and a robust point. A mathematically optimal point in a contour plot you could conceive as a pile of stones that is maximally high, maximally large, but it need not be perhaps optimally stable. In case there is a lot of wind blowing from the side, there is a risk that this pile of stones will fall apart. Whereas an optimal pile of stones will have some stability and resist, for instance, the influence of wind and rain and kids playing around it. It need not be maximally high or maximally tall, but it will definitely withstand a lot of perturbations and therefore be considered much more robust. We are using DOE technology, design of experiments technology, to estimate what is called a design space, and inside this design space we then try to pinpoint the location of this so-called robust optimum. Before we go into the software demo, I wish to dwell for a moment on some of the concepts that are floating around and provide the interpretation from the data analytics solutions side. So first of all, there is a term floating around known as the knowledge space. In our interpretation, in the geometric suite interpretation, you can say the knowledge space, that is the region in which you've done DOE, where you've done experiments planned according to an experimental plan. Then usually there is also something called or denoted or referred to as the design space. The design space is a much smaller volume or area located within the knowledge space, and this can also be a highly irregular volume. And this volume is then defined by our models, one or more models, and it is then the region where the one or more responses is according to specifications, also when considering uncertainty. So there is a very low risk of failing to comply with the specifications for the one or more responses. Inside the design space, there is sometimes also something that is called the normal operating space. And this is a smaller space or smaller region located within the design space. And this is usually then often the recommended ranges for operating or running the system or process. We are going to very shortly demonstrate how we are conducting or accomplishing robust optimization, but first of all, just an overview slide where we overview the approach in brief. If you want to know more details, you have to consult complementary webinars in this topic and perhaps also look into our training material. But basically what we are doing is that the design space or the design volume where we've done experimental designs is partitioned in sub-blocks, and the number of bricks or the number of intervals in which each factor is divided into is regulated by an adjustable parameter known as the resolution. And in each sub-block, we're then making Monte Carlo simulations. We're making predictions of the one or more y variables, and we're then counting how many predictions are in line with specifications and how many predictions of the responses are violating the specifications. And if we have a rather small fraction of predictions violating the specifications, then often set at 1% risk, then if it is okay with a very low risk of failing to comply with the specifications, we assign a green color, and if it's not okay, it becomes, so to say, a red color. And this approach will often give a very irregular and dimensional design space description, but we can have a full account of it and plot it following some tools that are available in the Model 12 software. And the robust set point that I was indicating and talking about will then correspond to a factor combination with maximal distance or margin to the acceptance boundaries of this irregular design space region. So with that little introduction in mind, we are now going over to the Model 12 software for accomplishing a demo of how we are conducting robust optimization, and the case study that we will be using is this truck engine application. Some of you may never have seen the Model graphical user interface in the past, but I have, like a good chef, arranged a little, prepared a little so we can see the basics. More details about how to initiate a DOE protocol, a DOE investigation, and how to analyze the data, the general workflow, the general mindset and architecture of the Model software is available in terms of the recording of the first webinar of this series of 11 webinars, so I refer to that recording. But you can see here that we have defined the factors. We have air, EGR, and needle lift, and there are the settings, and there are also some precision estimates that are known by the engineers, and these represent the uncertainties in the factor with which you can uphold the factors around the nominal value, and that is one source of uncertainty that can be integrated into or taken into account into the Monte Carlo simulations. We have the three responses, and we see that we have the maximum settings here. These are the specifications that I were talking about, and here we have the DOE protocol. For those of you who are after the details, I can say that this is a central composite phase-centered DOE protocol in 17 experiments, the CCF. What we're then doing with the data analysis is to find relationships between the three factors and see how they combine in influencing the three responses. And the usefulness and the reliability of the different regression models are then summarized in our so-called summary of fit plot. And the summary of fit plot has 4
bars for quality checks, you can say, for each response. And the meaning of these bars and reference values for them is beyond the scope of this presentation, but I refer to our surrounding documentation, the textbooks and white papers and the user guide, and also our online trainings and open trainings to find out what they mean. In this case, we have very good and reliable regression models. In the PowerPoint part, we were looking at what we call response contour plots as a means for interpreting how factors and responses are correlated. An alternative representation is given down here, where we can also look at the regression coefficients. So we have then optimized the profile of regression coefficients with regards to each response. We have the fuel, the NOx, and the soot regression coefficient profiles. After you have done that model interpretation, and that is nowadays possible to do more like in a black box fashion, we are introducing a new concept called one-click analysis that will become available in the release soon coming out of the next version of the model software solution. So stay tuned and watch out for that tagline, one-click analysis, if you want to know more how you can automate the data analysis part. After you have derived these models, you move into the optimizer, and that is where you are really entering into the design space capabilities and robust set point calculation capabilities of the model software solution. The optimizer you can say have a number of different elements, and one element is a part where we are setting the specifications for the responses. I have now defined maximum settings for technical reasons. We also need a complementary target value that is slightly smaller than the maximum setting. So we will then see where we will have the predicted values in the graph here later on. And then we have another element or another part of this tool that deals with the factors, and from the beginning we will allow the optimization searches to look in between the ranges where we have done experiments, but we can also modify the low limit and high limit and start to extrapolate rather than interpolate. So we simply click the optimizer, run optimizer, and it will now conduct something called Simplex searching for locating combinations of the factors where the predictions of the responses are in line with the specification. Every such combination of factors, you see it gives 20 proposals. Every such combination of factors is called a set point, and the set point can then be ranked according to different criteria. And we can also explore the different set points. And if you look down here in the graph part, you can see that some of these set points can be quite different as far as which factor combination they have converged to is concerned. So really you have to look into the different optimal set points. So these different proposals, they are optimal but not necessarily robust. It means you can think of the pile of stones that was very high but perhaps a bit unstable. If you want to find a more robust set point, we have to launch a specific command. We have to include a couple of settings. We will run with the prediction interval rather than the confidence interval. And then here is where you can set how many sub-regions you are dividing, or how many intervals you are dividing each factor range into. I have now configured this to take around 30 seconds, just not overly long in terms of this webinar. You can easily be on the hour scale or even overnight scale if you have 5-6 factors and are running on the highest resolutions and with the maximum number of iterations for each grid point in the grid that you are creating. If model will find a robust set point, which it did when I was rehearsing this earlier today, it will give a sign and it will add that set point in the list of possible set points and use the uppercase R for robust. So a robust set point has been found and it has been added to the list with the notation R here. That means that we can now go over to the Design Space Explorer tool and start to visualize where it is in the factor space, and exactly what let's see if we can have the same things on the axis. We should go for, here, we should go for EGR and air here to have the same representation. And then it depends a little bit on where the third factor is converging, where you will see the robust set point. So here we have the robust set point in the middle of the, or at the gravity of the green region or green volume. It is in this case appropriate to talk about a green volume because we are actually having a three-dimensional problem. It's not just air and EGR, but also the third factor, needle lift is there, and we can also do a sliding here across changes of the third factor, so we instantaneously see how things change, and where we have the crosshairs, that is where we have the robust set point, which has a maximum distance to the borders of the green volume, you can say. Down here we also have more information on, I can do like this so we see better. Down here we also have more information on the exact coordinate that has been found, and we also have ranges for the factors, what is called the hypercube low edge and high edge, and we also have that visualized over here. So MODE will provide two complementary estimates of factor ranges. We have the green field down here, which represents the mutually largest ranges for the factors within which they can simultaneously be changed. Or we have also the black T lines, which represent the individual ranges for the factors. So either we talk about the green fields, which are the mutually largest ranges for the factors, and here you can change the factors freely without any restriction. And if you look at the black T lines, it is an individual range for each factor, and then that range is applicable for that particular factor, given the condition that all the other factors are locked at the coordinate of the set point. And the green fields here, down here in the hypercube range, they represent the largest irregular geometry that you can insert into the irregular design space volume, and I will come back to that in the PowerPoint part.
So we are now back in the PowerPoint environment, and the first rounding off slide is then just once again repeating this possibility of the Model 12 software to estimate this highly irregular region that is the design space. And we have also shown how it can be restricted in fact by various adjustable parameters, the factor precision, model errors, specifications, and other settings. And we also discussed that a full account is possible to obtain through what is called the Design Space Explorer list. We also have seen that inside the main output tool, the Design Space Explorer tool, there is a plot where we inside the irregular green area or volume is also inserting a hyperframe that is indicated by a dotted line. And this design space hypercube then represents the largest possible regular geometrical structure that we can insert into the regular design space. And then we have the robust set point marked, and it is then at the center of gravity of that regular hypercube. So just a little clarification. We have also discussed and seen in operation some of the basic ingredients contributing to making the robust optimization a reliable approach. We have to consider process variability, the reproducibility of the actual process. We are considering uncertainties and variabilities both in X and Y. We are also considering the uncertainty interval estimates for the predicted Y. There are different ways to express the uncertainty. We have tolerance intervals, prediction intervals, and confidence intervals. And if you're really doing this on a very sophisticated level, we can also, inside the Model 12 software, choose to consider whether the responses are correlated or not, although we did not discuss this in that particular setting in the demonstration of the software. So all in all, what we have or what we're doing is symbolically summarized by this little scheme or this little graphic. We have uncertainties in the factors. Through a transfer function, which is the regression model, we're estimating a prediction for the response, and by also considering the uh, flaws of the model is never fully perfect. We can have a residual standard deviation in the model, and we may also have some flaws in terms of the configuration of model terms in the model. And using these uncertainties, we are not only providing a predicted value for the yield, we are even providing a distribution of predicted values, and that distribution can then be compared with the specifications for the responses in question. So Model 12 is really a state-of-the-art tool for design of experiments and quality by design. It is there to help you get it right from the start. Mod is an important ingredient in the geometrics suite, and if you're looking at the geometric suite from a bird's eye perspective, you can say that the whole ambition of this suite is to help our users to see what others don't. Removing the names of the softwares and focusing on some of the core objectives of data analytics, we can say that with the toolset that is available inside the geometric suite, we can address in a reliable and transparent way the descriptive data analytics questions, the diagnostic, predictive, and prescriptive data analytics questions. And we were also discussing how these data analytics questions / objectives fit very well in with inside the objectives of the geometric suite in the first webinar. So trying to round off, we can say that the objective of the geometric suite is to help our users, clients, to do data mining of their data in their databases, to plan informative future experimental scenarios so that you get out maximum value from your experimental campaigns. We would like to be able to help our users, and we are able to help our users to find the golden nuggets, the valuable nuggets in their data, and understand how to capitalize on those, and outlining how our clients and users should perform in order to change a little and thereby grow a lot, you can say. In the next webinar in this series, which is the third part, we're going to zoom in on the second tool in the geometric suite, which is the Easy Analytics software for everyday data-driven decisions done in a very efficient manner. So I hope to see you on board that webinar, which is going to be provided in a few days from now. So for the time being, I thank you all for your time and attention, and I wish you a continued nice day and afternoon. Thank you very much for your time and attention.